Now, not all these ratio tests will give us an infinite radius. And so we're going to have limited domains for some of these examples. So this is one where our domain is going to end up being limited. So we're going to our first step is we're going to use a ratio test to work out the interval of the radius of convergence. And as note, there's my x term. Notice it has no horizontal shift, so we can, at this point, assume our center is at 0. So I'm just going to maybe make a note of that there. C is equal to 0. There's no horizontal shift. And then I'm going to set up my ratio test. The limit as n approaches infinity. Okay, so this gets a little bit complicated, but because there's lots of terms, we're going to have -1 to the n plus 2, and then we're going to end up with x to the n plus 1 over n plus 1. Okay, so that's my an plus 1. In the denominator, I need -1 to the n plus 1, x to the n over n. Okay, so that all needs to be less than 1 to establish my radius. I'm going to group a bunch of these terms together. So the n plus 2 over, sorry, -1 to the n plus 2 over -1 to the n. I'm just going to write that as -1 to the power 1. Okay, and then I'm going to group the other terms here. The x's are going to go together. So I'm going to write it as x to the n plus 1. So I'm going to write that times x over x to the n. And then that's going to be grouped together. And I have n over n plus 1. And that's going to be grouped together as well. This all needs to be less than 1. Okay, so that -1 becomes not relevant because it's inside our absolute value. So we're not going to worry about that part. Some parts cancel out here. We have x to the n canceling x to the n. And so I have two parts of this limit. So the limit as n approaches infinity, the -1, which is not going to really count. I've got an x part, and then I have the n over n plus 1 part. Okay, so now I'm going to have to evaluate my limit, and n over n plus 1 to the as n goes to infinity just equals 1. So I end up with this, that x term, this becomes 1, the absolute value makes that -1 not relevant, so I have this situation here, where absolute value of x has to be less than 1. So this then establishes my radius of convergence. In this case, my radius is going to be 1. So it's centered at 0, and I'm going to have 1 to the right, 1 to the left. So this represents my interval so far. My x has to be less than 1 and greater than -1. This represents my radius of convergence from my ratio test. Okay, the center is at 0. So if we want to talk about the interval, our interval is centered at 0, radius goes 1 to the right, 1 to the left. We've established this part of the interval so far. We now have to test the endpoints. So when I look at this, I'm just going to again show that I have it centered at 0. Okay, just going to draw the number line visual for it. It's centered at 0, and my radius is 1 to the right. We need to test that endpoint at 1, and then 1 to the left, and I need to test that endpoint at -1. Okay, so this is now a situation where we have to test endpoints. And we want to use, we need to test the endpoints by plugging in the x values at the endpoints. So I'm going to start with +1. So I'm going to test x equals 1. And I'm going to plug that into the original series. So n equals 1 to infinity, -1 to the n plus 1. That's going to be 1 to the n over n. Now, what this ends up being is, this is, that 1 to the n really doesn't do anything. It just becomes 1 over n. And maybe just so that you can see a little bit more clearly, I'll put in the relevant parts. It becomes an alternating series of 1 over n. This is an alternating harmonic series. This converges. Okay, so that means then it is convergent at x equals 1. That means we include that endpoint as part of our interval. We need to now then test the other endpoint, -1. So we're going to test x equals -1. So we end up with n equals 1 to infinity of -1 to the n plus 1, -1 to the n, and this is all over n. Now we're going to have to kind of simplify that. So this becomes -1 to the 2n plus 1. Okay, -1 to the 2n plus 1. Now 2n plus 1 is always odd. Okay, 2 times anything is even, and any even number plus 1 will be odd. So -1 to the 2n plus 1 is always going to be negative. So we can simplify this as a harmonic series of -1 over n. This is a harmonic series. This is divergent. So this is divergent. That means we do not include the -1 endpoint, okay, because that series does not converge when x is -1. So this then represents my interval of convergence. The first thing I did, I kind of want to know where the center is. I've used the ratio test to determine the radius of convergence. That establishes the endpoints of that interval. Lastly, I test the endpoints to see if they converge. I do that by substituting the endpoint value of x into the series and then do some sort of convergence test. And that convergence test can be any type of test. It could be just a comparison test. It could be just a power test. It could be any type of test you want to use. It doesn't necessarily have to be formal, but we need to establish if the endpoint converges. So now that I know the endpoint converges, I know that my interval is going to look like this. It's going to be greater than, not equal to 1. It's got to be less than and equal to +1 as in my interval notation, I can write it like this. Okay, it is half, what we would consider half closed, because it's closed on the right endpoint and it's open on the left endpoint.